if we could increase the reflectivity of the Earth by 0.5%, we've solved the problem. And one way we might be able to do this is to change the reflectivity of clouds, and that's what these ships are doing.
Taking the time to be here tonight. We're near on through midway of this COP here in Glasgow, and certainly you've all heard the dire situation that we're in, and indeed, that's not to discount it. It's very dire indeed. But we're here tonight to offer you a bit of hope on this program that we're bringing you on Marine Cloud Brightening. And this is a climate emergency forum program in conjunction with Facing Future TV. And we have a few special guests tonight. And I'd like to introduce our main speaker of the evening, who's Dr. Stephen Salter. And he's a Emeritus Professor of Engineering Design at the University of Edinburgh and has been one of the leading voices of the Marine Cloud Brightening movement. And he's here to teach us a bit about it and offer us a glimpse of the promise of hope in this movement. So without further ado.
Thank you. The greenhouse gases are increasing the amount of heat we're retaining by about 1.7 watts per square meter. And the sun is putting in about 340 watts per square meter over 24 hours averaged over the Earth. So if we could increase the reflectivity of the Earth by 0.5%, we've solved the problem. And one way we might be able to do this is to change the reflectivity of clouds, and that's what these ships are doing. They are squirting out very, very small drops of filtered seawater, 0.8 of a micron diameter. These going out horizontally, but because of the cooling of the evaporation of the air, and they evaporate, they will be going down. They won't go into the sea because the air is not going into the sea, and they're glued into the air. But they'll warm up from the sea, and then they'll get up to the cloud level. And the job they can do is really quite useful. They are cooling. I've got different areas here for an El Nino or a hurricane or an Arctic ice. And the bottom line of there is the number of vessels that we would need to work at full power, maybe they won't all be, for doing jobs in different periods. And you'll see that for reversing sea level with 20 years, if we did that in 20 years, we'd need 400 of these ships to do it. And if we wanted to save the Arctic ice, we just want 42 vessels, which would have to do the job in just 60 days, on the other side of midsummer. This is why we have to do it. You can decide what the chances are of putting carbon dioxide concentrations back down. That's the Keeling curve, which must be very frightening. This is the amount of energy that's been going into the deep oceans, and a zettajoule is about twice the total human energy consumption of all forms of energy. I didn't know what a zettajoule was until I started this. This is showing different seawater temperatures over the oceans. Complicated, interesting, and we may need to do different things in different places. That's the separation between the different oceans. Now, the number of dots there is a representation of the total solar input. And if you look at the tiny little thing down there, that's the human energy consumption in all forms. That really makes you, it hits you in the gut with the difference between the solar input and what we're actually doing. There is a rather familiar slide, but if you look at this one, you'll notice that the top arrow is going to a rather white bit of cloud, and the lower arrow is really a grey bit of cloud. This chap here, a chap called Sean Toomey, who really started all this business, was very interested in why some clouds were whiter and sometimes were grey, and he was able to fly over them and measure the light coming down from the sun and the reflection coming up, and he could fly into them, and he could scoop up samples of cloud drops and see how big they were and how many there were, what the concentration was. And he produced lots of really heavy algebra, which you can condense into one slide. The vertical axis is different amounts of power or albedo or reflectivity, but the key is the horizontal line, where it's the relative number change of the cloud drops. So you can choose the amount of energy that you want to reflect up and down the vertical lines, whether it's the cloud or at the top of the atmosphere. You slide along until you hit the slope line, and then you drop down, and that'll tell you how much you want to multiply the cloud drop concentration. There is a photograph showing, I've got another copy of it here, showing the effect of larger number of smaller drops being white and the small number of big drops being grey. Those are glass balls, so it's the same material and the same shape, just different sizes. 4 millimeters on the left, the grey one, and about 40 microns, 100-to-1 ratio. This chap here knew all about this, and he suggested that we might be able to cool the Earth by spraying seawater. And his idea. And you'd have thought there'd be a fairly even distribution of drop sizes in the atmosphere, but there aren't. There's 3 different modes, and the coarse mode is not big enough to show on this diagram. We want to spray where the red arrow is, which is 0.8 of micron. That would, if that evaporated down to a completely dry solid, it would be about 200 nanometers, and we think we need a rather narrow spread on that. This is a plot of all the estimates made of all the amount of seawater that's been thrown up into the atmosphere, plotted against the year that they were made, all right? And you can see that it must be a rather difficult thing to measure. The average value is a little blue circle there, and if you look carefully, you might just see a thickening of the black line of the horizontal x-axis. And if we were trying to have 1,000 of our vessels working flat out, full power, they would be producing the thickness of that line. So it's not the amount of water we're putting up, it's the number of successful nucleations, and that depends a bit on getting the right size. That's what they look like again, and that's what the engineering would look like. You won't be able to see any of the detail of that at this scale, but it shows that we are really well ahead in choosing seals and bearings and the thicknesses of all the sections. And they're driven not by sails, but by things called Fleckner rotors. And this was built in 1926, the original ones, and they're now being introduced into quite large ships, and they're saving quite large amounts of fuel. This is a result of some work in Norway, where they were a bit more intelligent than most of the climate modelers, and they decided it would only be a good idea to spray where there were low clouds over the oceans. And what they did was to increase the nuclei concentration by 50%, which is quite a modest change. And you can see there's a really big concentration of cooling right up in the northern areas, which is extremely welcome. And that's on the right-hand map. And then on the left-hand map, you can see what it's doing to precipitation. and you'll see that there's greeny blue bits in the Sahara and Australia and Mexico and South Africa. So it's increasing the amount of precipitation in the drought-stricken regions. And where it's reducing precipitation, it's over the sea where nobody really cares very much. If there are small islands there, we could perhaps provide them with desalination plant. And another thing we can do is to cool the sea to moderate hurricanes. And that map is showing you where the hurricanes start and where they get bigger. And the ones that get publicity are the ones that hit America. And you see they usually start in the Cape Verde Islands over on the African side. And what we could do would be to have fleets of vessels that were cruising around, starting in November, and through the year, they would be measuring the sea surface temperatures, and you'd adjust the number of them to match the required choice of sea surface temperatures that was chosen by the governments of the countries in that area. No one's brave enough to say, we'll promise you no more hurricanes, but they can say, we'll get you down from 26.5 to 23, and you prepare somehow how close we can get. And there is a table again of all the jobs that we might do. I think these would depend very much on the initial concentration of nuclei and the drop life of the ones that we spray. And I'd like to put a big factor of safety on that, but they're not absurdly out. It's very difficult to get a cost estimate of anything if someone loses their job if they revealed the secrets of a commercial company. What you have to do is to look around for something that's similar in production rate and in power and weight and working conditions. And the only one I've been able to find so far to help us estimate the cost of spray vessels is the Flower-class corvettes that were built for the Royal Navy in 1940. And they cost £60,000. And if you index link that till today, it's about a factor of 50 increased. Chief scientific advisor was paid 600 quid a year, R.V. Jones, who bent the beams that were navigating the Luftwaffe. And if we wanted to have a fleet of 800 of those, it would cost about £240 million a year to pay the bank and do the maintenance. And I picked 800 because I'm told that the cost of security for this conference was 250 million. So it would be cheaper to have a fleet of 800 corvette replacement spray vessels than to have this conference. Now we'll hand back.
Thank you. Thank you so much for that, Professor Salter. I'm particularly astounded at the affordability of this option. Less than 250 million pounds a year to enact this, and it's amazing that just by brightening the clouds themselves, which this technology promises to do, we can increase the albedo and thereby decrease the global warming averages.
And the money we save could get more policemen.
Right, exactly, exactly. So thank you so much for that. And now I would like to introduce Dr. Peter Wadhams to my left here. And Dr. Peter Wadhams is a professor emeritus of ocean physics and head of the Polar Ocean Physics Group in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. He's best known for his work on sea ice, and he's author of the well-known book, A Farewell to Ice. So with that, I'd like to turn it over to Dr. Wadhams.
Thank you. Well, there are many aspects of marine cloud brightening which make it very especially attractive as a means of cooling the world or preventing it from warming so much. The first one is that comparing it to a technique which has been tried but I find rather less attractive, is that you can turn it on and turn it off. When you want to produce the cloud brightening effect, you switch on the pumps. You have N ships, each of them using these fine nozzles to pump finely divided seawater particles into the cloud. But as soon as something happens that you don't particularly like, for instance, clouds are coming up in the wrong place or not going to the right place, you can simply stop pumping and stop. So you stop and start, whereas with aerosols, which is the other technique of geoengineering that's been tried, you have to release a large amount of very fine aerosols which might be toxic into the upper atmosphere, and then you just have to sit there while they gradually fall out, and they may fall out in a way that you don't like, that will do something dire to the world weather systems. So it has the advantage of immediate control. It has another advantage that it's non-toxic, and the level of knowledge and, well, dare one say, intelligence of a lot of the public to doing with climate-controlled efforts makes them terrified that if you put aerosols into the upper atmosphere, everybody will be poisoned. And so there's no danger of that with water, seawater. The other thing is that the fleet of ships that you need, which, as Stephen has shown, is remarkably small number of ships, remarkably low cost, but they can be dispersed or concentrated in the way that you want, that will fit your model of what you need to do if you want to focus the cloud brightening on one particular region. One that's been modelled very intensively is the Arctic, and the idea there is that you focus the input of cloud brightening into clouds that are heading for the Arctic, warm in that way, cool down the Arctic, and prevent it from doing some of the things that we mentioned at the last talk, which is melting too rapidly and causing release of methane. We can actually try to refreeze the Arctic to some extent, and the models say that this would work. It doesn't completely refreeze, but it does go a long way towards slowing down the impact that the warming water would have on methane release. So in many, many ways, it's attractive. Stephen's also mentioned hurricanes as well, and it's the role that cloud brightening would have in moderating hurricanes and other weather systems. It's acting as a moderating influence everywhere in the world. So given all these advantages, it is a negative miracle, I suppose, that this hasn't been taken up as the most important and most fully supported method of geoengineering for restoring the world's climate. And I don't understand why that is, and I think we hope that in the greater understanding that we now have of climate change, and hopefully the greater enthusiasm and the greater amount of funding now available, as we can see from this meeting, that it will find its true métier at last, and especially since the person developing it comes from this very country that is sponsoring the COP. So I'm hopeful that at long last marine cloud brightening will get fully supported, and it doesn't do away with carbon dioxide, of course. No system that's geoengineering does that, but it will cool the climate enough to prevent some of the worst extremes from happening. It won't prevent the ocean from getting more acidic, which is a problem that we get from now from acidification of the ocean from extra carbon dioxide dissolving. But it will do a lot, and it could be the sticking plaster that would hold the fort between doing nothing about global warming, which is what our present policy, unspoken policy, seems to be, and the policy of actually taking carbon dioxide out of the air in a systematic, or out of the sea in a systematic way that will bring down CO2 levels. So this could be the sticking plaster that does the job of keeping us all surviving until these other methods come along. So I recommend it strongly.
Thank you so much for that. I really like, in terms of geoengineering, as I mentioned in a program yesterday, it's sort of the word that dare not speak its name. A lot of people are frightened by it, and I myself can understand that. But what is so enticing about this particular geoengineering scheme is the flexibility of it. And as you had said, Dr. Wadhams, that this idea of immediate control, this ability to turn it on and turn it off. And in fact, since it's dependent on these boats that can travel and go to various problem areas, it's targeted, right? So it's not something that it's like, okay, well, let's emit something into the atmosphere and see what happens in a few days. It's very targeted, it's very neat, it's very controllable, which I think makes this something that a lot of people would be amenable to. So thank you so much for bringing those ideas to the fore. And next up on our panel is Paul Beckwith. And Paul is a climate systems scientist who has taught at the University of Ottawa in the Laboratory for Paleoclimatology, as well as at Carleton University. He's a well-known scientist in this field and has produced a tremendous amount of videos on the subject, over 1,000 as a matter of fact. So, Paul.
Thank you, Regina. I used to read loads of fiction novels, horror novels by Stephen King, very famous American author. He's written over 50 books, horror books, but I don't get the same feelings of frightness and reading his books now. All I need to do is read a climate paper, a peer-reviewed climate paper, either on, the Antarctic or on extreme weather events or what's happening in the Arctic, global food shortages, biodiversity, extinctions, all this stuff. I mean, that's, the horror in these climate papers far exceeds any fiction that's been written. So one of these papers that I'm talking about, very frightening paper, just came out a few weeks before this conference, and it argued that the average reflectivity of the entire planet, which is nominally known to people as about 30%, it's difficult to measure. You measure it from satellites up above the Earth. The paper argues that they've measured that reflectivity has decreased from 30% to about 29.5%, a drop of about 0.5%. And how they measure it is quite fascinating. Next time you're looking up at the moon, the bright crescent that you see is called moonshine. The sun hits the moon and reflects to the Earth, and our eyes see that crescent as bright. The dark part of the moon is called earthshine, and the sun is actually hitting the Earth, reflecting off the Earth, going up to the moon, reflecting back to our eyes, and we can see it often on clear nights. And by measuring the reduction of that earthshine, we can infer the loss of the reduction of albedo or reflectivity of the Earth from the 30 to 29.5%. Now they say that they think that this has occurred in the last 2-3 decades because of less clouds in the Pacific Ocean in particular. There's a number of reasons why they think that there's less clouds, but probably the most significant reason is that there's a lot less phytoplankton in the ocean, maybe 50% less now than there was in the 50s. phytoplankton naturally produce chemicals, one that's like dimethyl sulfide, which then rises into the air above the ocean and acts as cloud condensation nuclei. Or there's also other phytochemicals from the plankton, as Russ George, an expert in that field, explained to me last night. So basically, the Earth is getting darker. We know the Arctic is getting darker a lot because of the loss of Arctic sea ice, but it turns out that the overall planet is getting darker. So this marine cloud brightening method is a way to take the existing clouds and if you put in cloud condensation nuclei into the atmosphere over the ocean and make their size a specific size, then the cloud droplets that form are much smaller. So the volume of water in a cloud is enormous. You're not adding to the volume, but you're making the composition of the cloud being very, very small droplets as opposed to large droplets. If you see an approaching cumulonimbus storm cloud, it's very, very dark. The droplets are very large and heavy, therefore, and you know that there's going to be rain occurring. So what this method does is, as Stephen showed here, is you make very, very bright clouds. Like your right is the very small particles, very small particles. So it's very reflective versus the glass vial on the left, where you've got a much larger particles and much darker, much less reflective. So the idea of spraying seawater through nozzles, you can tailor the nozzle size so that you get water and the salt enclosed within the water, and then when the water evaporates, you get very specific size salt crystals, which he's studied carefully as to which size is optimum for the brightest clouds. There's also a lot of other gains because the lifetime of the clouds is much longer if the water droplets in the clouds are much smaller. And the reflectivity, of course, is much higher, and you can change the reflectivity of the clouds in the regions that will benefit you most. For example, if you want to protect a coral reef, you can generate lots of clouds downwind, and then the wind will blow these clouds over the region where the coral reef is and cool the water underneath. If you want to cool the Arctic, you would put them up in the north. So the warm Gulf Stream coming across would then be shielded. You're putting basically an umbrella up on top of it to reflect away sunlight to cause cooling. Now, climate change is really a warming ocean problem. Over 90% of the heat coming into the Earth is heating the oceans. So if there's any way we can cool regions of the ocean, it's crucial. And this does not affect the land at all because there's very few cloud condensation nuclei over the oceans, but there's tons of it over the land and near coastlines. So you're not affecting things on land, you're just tailoring the clouds over the oceans.
Thank you so much for that clarification, Paul. And I believe Dr. Salter?
It is a little quick question for you to do for your homework. You want to work out the energy that is reflected by a cloud drop, which will depend on its projected area. About 8% is reflectivity, depending on wavelength. Compare that with the amount of surface tension energy that you needed to make the tiny little nucleus on which the drop grew. The cloud drops through up to 25 microns, and we want the surface tension to make something that's about 0.8 of a micron. And the number, I want you to be sitting down when you do this calculation. It's tens of millions. And it's that really makes this energy ratio, makes the project work.
Well, thank you so much for that. And thank you, everyone on the panel who shed light on this really interesting geoengineering program. that seems to hold so much promise. And in the spirit of giving thanks, I'd once again like to thank you for being here and thank the following organizations who've made it possible for us to present here tonight. That includes the Interfaith Center for Sustainable Development, the International Society for Ecological Economics, and the Buddhist Tzu Chi Foundation. So thank you to them, and thank you to y'all, and have a good evening.